Um, all right, so I'm Henrik from Autodesk. Maybe I should use this one. Is it better? Yeah, yeah. That's, and my co-presenters are Ashwin, also from Autodesk. Unfortunately, Caroline couldn't make it here, but we have Tom from Pixar presenting Pixar's portion of this. So this work has been a collaboration between Pixar, Autodesk, and Adobe. We did present some of this at Vulkanized, so if you were there for that presentation, some of this is going to be a rehash, but we have progress since then to share with you guys also. So unfortunately, we didn't have anyone from Adobe here today either. So I'll start with a little bit of an introduction to what Hydra and Storm is and why we think this is very important to Autodesk and why we're investing so heavily in it. Ashwin will go a little bit deeper into the work that we are doing on the Autodesk side. Our tooling and also software rendering through LavaPipe has been something that we've been looking at quite heavily in the last few months. And then Tom will talk more about the Hydra graphics interface and what we've done there to kind of migrate from an OpenGL pipeline to Vulkan. So just for Autodesk side, we will be talking about things that are unreleased, forward-looking things. So please don't make any purchasing decisions on what we're presenting today. So Autodesk, when we're here at SIGGRAPH, we highlight a lot of our media and entertainment products, Max, Maya, Arnold, Bifrost, and many of those products. But we're a quite big and diverse company, so our biggest industries are actually AEC, architecture, engineering and construction, and product design and manufacturing. So we have 100 or so products across these three industries. Obviously, there are some differences between the industries, but they all have in common that they need high performance, scalable graphics and run on multiple different platforms. So that's where Vulkan comes in. I should mention that earlier, but Ashwin and I, we work in the graphics platform group at Autodesk. So we work with all the major Autodesk products across these industries and developing the graphics system that drives the viewport. So across these products, we have a need for a wide range of graphics capabilities. So it's not just pretty pictures with global illumination and shadows and fancy materials. We need to cover everything from like 2D blueprints with lots of lines and text and so on. And those can be highly complex. Like there's a lot of primitives and a lot of messy data. So it's pretty challenging to get that to scale well. So that we need Vulkan for that as well. Then obviously we have a lot of like 3D modeling workflows where there's some shading going on, but you don't want to have too much because that could just get in the way when you're like doing surfacing design or things like that. But most of our viewports also need realistic rendering, so the higher fidelity we can produce in the viewport, the better. So most applications have like all these styles, and you switch back and forth depending on the type of workflow you're doing. But even AutoCAD and Revit and those products, they have photorealistic views. And on the Max and Maya side, you obviously have views where you don't necessarily have textures and lights and so on. So most of our products have been around for decades. So this is an ongoing journey to always try to stay on top of the latest evolution of graphics. So our current objective is basically to migrate all our products to the most modern generation of APIs, Vulkan, Metal, DX12, and also Web GPU. We do want to leverage open standards and open source as much as possible, like across the whole graphics stack. These are just a few, but we were talking about the viewport here. So USD and Hydra, MaterialX, OpenPBR, OpenColor.io are some of the main ones. And one desire we have with like modernizing our graphics stack right now is to make it more decoupled, so we can more quickly roll out. Like I mentioned earlier, we have 100 products, so if we have a new feature, we don't want to integrate it 100 times in all those different products because it takes forever. So if we can have a clear separation between the applications and the implementation of the graphics stack, we can roll out new features much more quickly if we can deploy them in the stack and it is not really directly visible into the application what happens there. So, and then we also have a need to run on multiple platforms. So Windows, Mac, Linux, a lot of our products are on all three. Then mobile and web is growing markets for us. So both iOS and Android, and then web with Web GPU. So, with Vulkan, we can at least hit Windows, Linux, and Android here. So if we look at kind of these objectives, that has kind of led us to the decision to base our viewports on Hydra and Storm. So Hydra is this decoupling layer that can kind of separate how you describe the scene graph from how you render it. So if you were here for the Nari talk, it's the same idea. Hydra has been around for quite some time in the Pixar pipeline, and so we had already started building our stack on Hydra when Aurora was in its infancy, but the principle is the same. So you describe the scene graph to Hydra without having to know what renderer you have on the other side, if it's a rasterizer or path tracer, or if it's using Vulkan or DX or what have you. You can have multiple different streams of data, going to Hydra from different data sources. It could be USD data, it could be GLTF, it could be your native scene representation in your application. And then on the other hand, other side of Hydra, you have the render delegate. So you can write your renderer towards an API without knowing where the scene data is coming from. So the main one we're going to talk about today is Storm. So that's the open source rasterizer that comes with the USD library that Pixar open sourced in 2016. There are a bunch of others, both from Autodesk and third-party Hydra render delegates. Aurora we presented last year at the Birds of a Feather. I'll have one slide on that, but the focus of today's presentation is on Storm. From Autodesk we also have Arnold, which is our production renderer for high-end VFX film type of workflows. It doesn't use Vulkan, so we won't cover Arnold in more detail here, but there's tons of other renderers, RenderMan, of course, and a bunch of other renderers that supports the Hydra render delegate API. And what Tom is going to cover more later is the Hydra graphics interface, which is basically the RHI that abstracts. It started off with OpenGL, but now, from Autodesk, we're focusing on the new generation of APIs, or new in quotes, but for Autodesk, it is kind of new. There's not too many products that have rolled out support for these APIs yet, but Vulkan, Metal, DX12, and WebGPU are the ones. So today we're going to talk about Storm and Vulkan. But I do have one slide on Aurora, so that's the renderer I showed here in the middle, because it is also uses Vulkan. So this is an open source path tracer, and you can use the QR code or go to the link below there. So it's for real-time viewport rendering. It's not a final frame production renderer like Arnold. It doesn't have all the bells and whistles. It's focused on performance and kind of the key features that you would need for either design visualization in a kind of CAD product, or a simple look dev in something like 3ds Max could be used for that as well. So the intent here is to have an open source path tracer that works on all the platforms. So we do support Linux and Windows today. Mac and Metal support is in progress. And it does have a Hydra render delegate, of course. We also support Material X and standard surface. Those are kind of the standard surface is the shading model. We're migrating that to OpenPBR. Don't have a timeline for that, but that's going to come in the future. We made some performance improvements since last year and migrated to the latest version of OpenUSD. So we have a new drop as of this morning that supports that. Mauricio had a longer talk at the BOF last year, so if you want more details on Aurora, you can find the recording on YouTube for the talk from last year's Vulkan Birds of a Feather. One final slide here before I hand over to Ashwin. So we're really taking an open source community approach here. We are very actively contributing to all these open source and open standards projects like USD and Hydra, Material X and OpenPBR. Quite active in all the different communities around these standards and open source projects. So we're co-founder of Academy Software Foundation, Alliance for OpenUSD, the Metaverse Standards Forum, and of course we've been now a pretty long time member of Kronos as well. And we work very closely with some of our main collaborators on the viewport stuff that we're talking about here today. So in particular, Pixar, Adobe, NVIDIA, and Apple. And this is really to advance OpenUSD and the Hydra ecosystem for the graphics industry as a whole. So with that, I'll hand over to Ashwin to talk a bit more about what we're doing here at Autodesk.
Thanks. Hello. So I'll cover most of the slides or content was something that Vipul from our AGP team had presented during Vulkanized a few months back. But I'll just try to quickly recap what he had shared and add more on what we've done since then. So to kind of reiterate on what Henrik shared, what our vision is. So our requirements for graphics are, again, we want to create large data sets. We have to visualize and author large data sets from 2D to 3D types. Our texture usages can vary. Our shading requirements can go from simple unlit to realistic, physically correct materials. So there is a wide range. And we have cross-API, cross-platform requirements, Windows, Linux, Android, Mac OS, web, cloud, and even virtualized environments. So that's something that I want you all to remember this. We want to leverage next generation hardware capabilities and practices. So a lot of our applications are still using the legacy pipeline workflows, and we need to change that to the modern practices. So translating Henrik's vision and the goals to real objectives for AGP, we want to build on OpenUSD, but specifically, we want to extend the Hydra abstraction layer and enhance Storm with capabilities that we need for Autodesk products. So that would be in like what we shared earlier, like lines, styles, all that kind of stuff. Right? Again, community partnership and support large model viewing with Vulkan. So our end goal here is to make Vulkan production ready for Autodesk products for Windows, Linux, and Android targets. And we would like to thank Apple for taking that lead on Metal for getting this ready for Mac OS and iOS. So a little list of feature requirements for the Autodesk graphics platform. This is again, there was a detailed, longer presentation at GTC from Adam Felt and Henrik. Check out that link. But again, we need viewport representations, multiple viewports, visual styles, UI integrations, materials, ray tracing, and then industry-specific workflows. So there are more details around this in that slide deck. But these are our key requirements that we need to support for successful integration of Storm in AGP. So to validate our features, what we have done now is we've built an in-house product. It's a standalone app that uses Storm. So we can still use USD View, but we can do this locally using our in-house application. So it can load models from mid to large range of models, and it's cross-platform. That means it runs on Android also for us, and Linux, and Mac, and all those targets. So what it does is basically it's got a very thin Vulkan layer, so it doesn't create any Vulkan resources. It uses AGI Vulkan to get all the resources it needs. But it does the composition and presentation layer. It takes care of that part. Now, what this gives us is an easy enough tool that we can use for debugging and doing analysis. So going a little bit into debugging and analysis, here are some tools that we use for our debugging purposes. And there are gaps here, but I'll kind of get into those. So for API validation, thanks to the Vulkan community, we use the debug and validation layers. We use a built-in, we built together a profiler that uses the timestamp query APIs to get profile information. And then as we need more and more detailed granular data, we start going into specific tools like GPU view for Windows, or using for mobile. We are still playing around with tools like ARM's the Streamline Performance Analyzer, which works very well. But we've not had much success with Qualcomm profilers. For GPU profiling, we use, again, the extensions that Vulkan provides. But for mobile, we have not had much success on any useful APIs. So if there is something, please let us know. For playbacks, RenderDoc, NVIDIA Insight Systems, it's like perfect, good tool for us. Similarly, for mobile, we use RenderDoc and AGI, but again, on Qualcomm, there are challenges. So we use vendor-specific tools when required, and the generic tools when required. But again, I want to thank everyone for these tools. These are really a time saver, and whenever they have helped us solve many problems. So one of the problems that or challenges that we're looking at is performance. So performance is the number. If we can't get performance, we cannot ship. So what we have seen is we are able to use those tools to gather captures, and we see similar access pattern problems in both mobile and desktop. So for example, I don't know if this trace here shows like there is synchronization problems. There's gaps between CPU, GPU. And it's the same thing that we see even on mobiles and tablets. So the strategy is simple: trace, analyze, fix, rinse and repeat. But we want to do it across platforms, just not make it specific to one target, but make the fix where it's applicable. So in desktop, if we can use a better API, use it. On mobile, try to find something specific if required. All right, now moving from GPUs to the next opposite end of the spectrum, software rasterization. So we have customers with large deployments, and they need CPU fallback. And they have many reasons, driver instabilities, GPU support. They have cost problems. They want to show that they are environmentally sustainable by not creating larger environmental impacts. Business continuity, like there is a problem with the driver, but they still need their users to be able to continue working. So software CPU fallback is a requirement. And the way we address this is in different ways. So for our product teams, what we do is we found that we can still use CPU fallback for small, well-scoped workloads. So when you're running on CPU, let's say on a product, you can turn off certain features, but still the user is able to load the data, make a decision, look at things. They might not be able to do high realistic rendering or something, but still they can get their job done. For engineering teams, this is, cost of GPU virtualization is still a challenge. So for CI testing, we can do CPU fallback for some of those. And a lot of us are using cloud-hosted environments. So we can use CPU fallback for some of those testing and workflows, and GPU testing when required. And a lot of our Windows users are currently using DirectX. And Warp is natively available. So they can switch to Warp as required. And so that's what our users are used to, having that workflow. So for us, having a stable software rasterization backup can become a go, no-go decision for Vulkan adoption, meaning a product might choose not to use Vulkan just because there is no software rasterization support. So this is important for us. So we brought this concern during Vulkanized, and we were initially using Swift shader, and because that's what we found was a common solution. And then we brought this up to Vulkanized, and everybody gave us nice feedback saying, hey, try out LavaPipe. It's cool, give it a shot. So we did. Meson is something new that we have not used before, but we worked through the build problems in getting LavaPipe to making it work on Windows. And we started using some of the samples that Sasha has to make sure that, does it really work? And yes, you get all these beautiful pictures. It's, good frame rate. It all works. So problem solved? Yes, maybe. So we threw it at Storm. And this is what we got, first pixel, right? And then we talked to Pixar, and through our joint efforts, and there were some problems in usage of Vulkan, and there were some problems in LavaPipe, right? It's all over. But through all that, we managed to get to the stage where we can actually render and even pass some of the Vulkan tests in Storm using LavaPipe. And this is on Windows. So this is really something that enables us to investigate further and get going on the Vulkan adoption. So, OK, the video plays. OK, so this is the latest test, which uses Vulkan through Mesa 24.1. And actually, Alexei Sapone from our team actually made some contributions to Mesa to get some of these things working. We have another PR in flight to get some performance from LavaPipe. But this video is me running USD view on a Windows machine connected via remote desktop from a Mac machine. Right? This is the workflow. This is the workflow that a Revit customer would do. Right? From here, they'll connect to a lab machine or something. And you can see it's interactive. I can move around. I can select. I can pick things. And so this is promising. So what do we do? So what we need next for LavaPipe? I mean, apart from the performance improvements. So all this testing is done using by overriding the ICD environment variable, right? But if you look at how a DirectX API works in this case, you just ask for a warp device, right? And so what we are trying to now look at is how do we simplify this workflow? How do we simplify loading LavaPipe ICD, make sure it's always available on device or on the system if possible, or maybe we need to ship it. But that's something we need to have a conversation about this. So to conclude, our next steps, get Vulkan ready for production. So make it spec ready. Make sure we get good coverage, unit testing and all that. Performance improvements, improve the synchronization stuff. Render graph, a lot of, that's the thing that we have not yet started even exploring. Optimizations. A lot of the modern APIs don't have geometry shader support, so we want to start using compute where applicable and improve that. Improve the algorithms for occlusion and HLOD integration. So there's a lot of things there. And on the software rasterization, like I said, improve the performance, deployment, and loader workflows. So with that, I'll hand over to Tom.
Yeah, while we're waiting, I'll just echo the utility of having a software rasterization fallback for us. It's we've got kind of fairly uniform hardware specs, but we're always looking for better hardware utilization. So if we have extra CPU time, then we can render with that. Okay, hey all. So yeah, my name is Tom. I work at Pixar, maintaining the Hydra project, which is the rendering component of OpenUSD, and it's the software. All the stuff is what we use for viewport rendering at Pixar. I am presenting some work and slides from my colleague Caroline, who couldn't make it to SIGGRAPH this year, but who's been working hard with Henrik and all the team at Autodesk to make Hydra run on Vulkan. And we wanted to share some things we learned along the way, since the OpenGL heritage in the Pixar code base runs deep, and we think some of the problems we ran into from coming from a OpenGL context make for an interesting case study. For a quick glossary and history lesson, so Hydra actually began its life as an OpenGL renderer for USD. We, in the meantime, have abstracted it to transport and evaluate data from multiple scenes on behalf of multiple renderers. It's kind of this, at this point, this interface layer. And so when we made that transition, the GL renderer was split off into Storm, which is, now the viewport renderer for, all the tools of Pixar. And so we later went through the similar evolution of abstraction in Storm, so rebasing Storm to work on top of HDI, and then moving past our initial implementation, which was, of course, HDI GL to add Metal and now Vulkan. We are working to shift to Vulkan internally, but the twist is, as always, without disrupting movie production or breaking compatibility with a ton of assets. So Storm was really originally written around OpenGL 4.5 concepts. In designing HGI, we wanted to help Storm get some of the benefit of the explicit APIs. So one, big difference, of course, is that, with Vulkan, the command encoders, pipelines, all those things moved out of the great state machine in the sky and became these first-class objects you can manipulate, and that's, this very powerful design concept. And given that, it's going to take a little while to get rid of all the GL code in our code base, we wanted to not constrain Storm as we're transitioning APIs. And so if you see up the bottom, we have a HGI GL encoder implementation, which just captures and queues OpenGL calls as closures for playback when you then go and dispatch that command buffer. And that's kind of a small concept, but then it starts even, with OpenGL, it starts letting you treat this as, there's a command buffer object that I can manipulate, and I can, kind of be building it in a different thread or anything like that. So it gives you a lot of flexibility API-wise. As we've gotten into the Vulkan implementation, we're still, of course, rooting out GL concepts in our code, as well as fixing up a lot of binding and sequencing bugs that didn't cause issues in the GL state machine, but which the Vulkan driver is rightfully unhappy about. I want to give a big shout out here. The Vulkan validation layers have been a huge help for this, finding all kinds of stuff for us, and certainly improving our GL implementation as well, as even as we're working to deprecate it. So finding things like accidentally binding buffers is the wrong type and stuff like that, which just went completely unnoticed by GL, but I'm sure we're not helping us. One fantastic issue that we run into our Vulkan implementation, I don't know if anybody else has run into this, is that Storm and more importantly a great deal of Pixar camera and image shader code and things like that assumes an OpenGL style projection matrix with a bottom left origin. Where do you place the origin? One of the great problems in computer science. So to support these matrices in Vulkan, our first idea was to keep the viewport origin in the new spot, but negate the height, which we thought was clever, but it caused a cascade of issues where then you had to negate shader derivatives and fragment positions, and then flip the sampling of some kinds of texture assets like intermediate buffers, but not flip others. And so it was like a bit like a game of whack-a-mole. So the eventual workaround we settled on was to keep the OpenGL style matrices with a normal Vulkan viewport, but flip the interpretation of the winding order. So basically invert the call style so that we could render upside down. So everything in HGI Vulkan is rendering upside down. And since this maintains a GL compatible addressing of the image, it's entirely internally consistent in Vulkan. There are no complications, and the only work we need to do is when we go to GL interop, or if we're presenting, we need to flip the image then. And of course, when we're going to GL, we're also kind of, that interop is also implicitly changing the origin position, so it kind of conceptually makes sense. Another big challenge, of course, has been our shader pipeline. So we try to keep Storm very declarative about pipeline features. For example, a certain Storm object might choose to use a certain normal generation mode based on what display style you're using or what kind of geometry it is. But the implementation of that normal generation mode is going to be contained in our, we've got a shader container format called GLSLFX. And so you'll have a name snippet in there, and so you might have, like a flat shading, vertex shading, patch evaluation shading or something like that. And so you find the correct name GLSL snippet and pull it in and stitch it into the shader program. But one of the issues with these shader snippets is that shader resources such as buffer bindings and interstage structures were originally part of the snippets themselves. So the snippet does have some important semantic knowledge of what resources it needs, but we want a language, shader language and shader API independent way of declaring a shader's resources and resource layout. Our solution was to extend GLSLFX to include an optional layout section for each shader snippet, declaring in an optional way, or declaring in a generic way what resources the shader is expecting, and then we process this at runtime to fill descriptors, which are then processed by HDI Vulkan, HDI GL, whoever, to they're produced by a shader generation code to produce compatible layout code to stitch into our shader program. This API-specific shader generation system is used for all of our resource access, including textures, buffers, fragments, and these descriptors can be introduced by these GLSL snippets that are really related to the pipeline of what exactly are you drawing. They can be introduced by material networks or anything else in Storm that's kind of contributing to your PSO. And this lets us deal with API-specific differences in declarations, built-ins, and keywords behind the abstraction layer. Another important thing that this abstracts for us is access to useful built-ins, like GL Vertex ID, for example, which is accessible everywhere, but with a slightly different name. So here we're following a pattern we use in Storm for shading signals. Storm will generate, has code generation to produce consistently named accessors for shading signals like color or normal or something like that, that you can sample in whatever shading stage you're in, regardless of whether you are pulling that data from a map texture, it's vertex varying data, it's per instance data. The idea is that the material author doesn't really need to care about this. It's kind of the responsibility of Hydra to provide access to that data however it's produced. Similarly, it's important to many of our pipelines, many of the things that create those shading accessors to have access to the vertex index or barycentrics or things like that, wherever they happen to come from. And so the HGI shader generation code will provide consistent Hydra names for these for, vertex ID, instance ID, all of that. And it will ensure that those are populated so that you can refer to them in downstream code. I will wrap up with screenshots because, screenshots are great. So these are all sets from Inside Out 2, loaded up in USD View 2408 and captured with Storm running on Vulkan. We've got Riley's bedroom, the friendship island, and then the bedroom of all the emotions over on the right. And so these are running in Vulkan. They've got all subdivided. There's some texturing, transparency, kind of all kinds of stuff in there. And these are all, of course, full of geometry. So it's been working great for us. Thanks so much.